Due to problems with the local microphone recording, I'll have to redub myself. Thank you very much for the opportunity to open the first ever second DENOG stage. I can vividly remember when I was visiting DENOG2, and the audience basically consisted out of as much people as I would have fit into one of the smaller meeting rooms of yesterday. Was an interesting time. A lot of people, a lot of stuff changed since then. So, let's have a look at what we are doing today. My name is Tobias, as I already mentioned. I'm doing all things network longer than I actually dare to remember. Part of the DENOG community for 20-ish years, visiting DENOG first at DENOG2. I somehow missed the first event. That happens. Spent a couple of time in the hosting industry, solution architecture for a value-added reseller, where you might met me in the past, and I'm now working as a solutions architect at PlusNet. You might ask yourself, who's PlusNet? PlusNet is best remembered by its brand QSC from back in the day, for one of the first DSL companies to build out in parallel to Deutsche Telekom. The network behind QSC, that was always us. We own our own access networks, both on copper, fiber, and wireless technologies. We actually connect third-party bitstream access by Deutsche Telekom or others, leased line and everything else to the network. We own our own Germany-wide IP and VPLS backbone network, which we need to connect everything together back to back. And we actually also own our own Germany-wide WDM network. That's the old WDM network that you might know from the gas line days, the active WDM network. And we use that to tie everything together, provide services across all of Germany. In the past, I've worked on a lot of different technologies, but one of the major things that always kind of comes along is pseudowire technology, and that's what we are looking into today in the incarnation of EVPN pseudowires. Let's have a look into what we will be covering today. First of all, we'll look into a problem. We then look into the technology which we probably use to solve our problem. That's EVPN. We need to look into a couple of boring building blocks. We'll then look into EVPN Flexible Cross Connect, which is hopefully the solution we'll then look into, which will solve all of our problems. And then we will have a quick look into how the solution is actually already used in the real world. Is anybody using it? How does it actually work? Is it only existing in unicorn land? We'll see once we get to that part of the presentation. We'll not be covering a lot of EVPN building blocks, but the things which are needed. So let's start with our problem. Every good problem starts with a customer. A bunch of customers are at the bottom, and you can easily identify them because they're wearing crowns, and we treat them like they deserve in our network. Let's now meet our favorite guy, our friend for the rest of the presentation, the aggregation router. The aggregation router is needed in order to aggregate all of these customers at one point in the network to make them, well, be able to access the network and the rest of our network. These customers are connected in different ways to our aggregation device. They could be connected to an MSAN, multi-service access node, which stands for all kind of boxes, OLTs, CMTSs or DSLAMs, depending on your access technology. They could come in via something called an A10 NSP. A10 NSPs are connections to bitstream access service providers. It's the standardized interface. Or they could come in via some form of leased line, physically connecting to some points in our network. Ultimately, they need to be aggregated somehow. They connect in there, and we'll need to get them somewhere. This somewhere is a services layer, the BNG. If you're lucky enough to already be able to do subscriber termination in your aggregation network, there was a talk last year from Fiona of Wobcom who showed how that's being done. You're not interested in that, but most of us, we still need to somehow backhaul our services to some central or multiple central BNG instances in order to terminate these services in there, and we do that by connecting back to these instances via MPLS pseudowires. These MPLS pseudowires need to be set up, and the connection needs to be done back to the BNG in order to stuff them into some service instances of some sort. Now let's have a look at a different perspective. Again, our now favorite device, the aggregation router. These aggregation routers typically have a number of ports in order to connect stuff, like the three categories we looked into earlier. And on each and every one of these ports, you basically have three possibilities to use MPLS pseudowires these days. Either they are per port, so a whole port is being consumed by a pseudowire. You can have a VLAN per port, or if you're already lucky enough and have a modern solution, you can have a per VLAN per group configuration option. But that's it. There's typically no way to interconnect between or across multiple physical ports. Last but not least, our second perspective, again, our aggregation router. We will learn to love him. He's there, but what if you not only need to connect to one destination, but three different destinations? In this specific example, it's a residential BNG, a business BNG, and an MPLS PE device. You might want to do this because you want to separate your customers. You might want to do that because you need to terminate them on different ones, but all of them are also connected via pseudowires, and you might need three pseudowires, one for each individual direction that you need to connect. Now let's put all of this together. Let's work on a couple of assumptions. The three target categories I already mentioned. We have a residential, a business BNG, and an MPLS PE. Again, due to the reasons I mentioned before, you might want to separate technologies. Let's say we have 12 aggregation routers in that specific region or in your overall network, doesn't really matter. All of them have 24 ports per aggregation device. And if we now start doing a bit of scaling math and looking into that, that's the number of pseudowires we are coming up with. Remember, you can only have pseudowires per port at best. You have three destinations. So with 24 ports and three destinations, you end up with 72 pseudowires on every one of these aggregation guys. And by having 12 devices across your network with 24 ports each, you're ending up with 288 pseudowires per BNG or central router location. That's quite a lot of pseudowires that you need to handle and take care of. This might or might not be a problem depending on how your network is being built, how you set up stuff, and how it generally is working in your network. But let's have a look at potential problems. First of all, the number of pseudowires can be a problem in itself. Your box might not even support the amount of pseudowires that you need in order to build whatever you've seen in there. Second thing is, the state of the pseudowires might be a big problem as well. First of all, you need to, instantiate them, get the routes up, protocols, whatever protocols are involved. But even worse, if you're doing Ethernet OAM, you need to also keep state of Ethernet OAM sessions for all of these pseudowires, which could become a burden pretty fast depending on the scale and the capabilities of your specific box in your network. Generally, resources could be a big problem. It might be number of slots in ASIC to actually handle these resources, VLANs, combinations of all of them. Really depends on what your box can or cannot do in order to support you in that endeavor. Changes could also be a problem. In order to deploy these pseudowires, you need to actually deploy configuration on both ends of the pseudowire. You need to deploy new configurations whenever a new port is thrown into the mix, which could become quite annoying quite fast because changes are actually points of failure. You could have problems when you create that, and you actually have to touch a lot of stuff in your network in order to actually deploy that. So, and that's my read up. I'll now hand over to myself after we've fixed the microphone problems.
Sollte gehen.
Okay, then let's continue. Not only pseudowires make problems, microphones as well, so you need to take care of that as well. Where there's problems, there's also opportunities. That's why there's a greenish problem space in the middle. If you want to do traffic engineering, that's where the TE tries to point to, you can do it per pseudowire if you have really, really granular requirements of actually traffic engineering. But if you want to do traffic engineering, you have to do it on every single one of these pseudowires, which also can become a burden. Remember, you need to do changes. Suddenly, you need to find a new way for that. That can be a bit annoying. Before we can dive into the potential solution for that problem, we'll need to do a bit of groundwork. This is not an exhaustive presentation on how EVPN works. I'm trying to scratch the surface there. So let's go over some potentially boring, because we've gone through that on a couple of occasions, but at least a brief history of the EVPN stuff. EVPN is a protocol. The E in EVPN stands for Ethernet VPN, was standardized in 2015 in the RFC, which is written on that page. It's a BGP-based control plane, which helps the data plane in some areas. Traditional protocols based on Ethernet VPN, stuff like VPLS, did something which is data plane learning. So every individual node needs to see a packet before it can actually instantiate a forwarding entry. With EVPN, once one of the guys saw that MAC address, it will instantly tell everybody else, and everybody's already pre-programmed. So it's basically a control plane that can spread data plane information. In its core, it's organized around the typical building blocks that VPN technologies before were built around. We have route distinguishers, we have route targets, we have a specific address family, next ray eligibility information thing. It's organized around a number of different so-called route types, and it carries additional information in communities, most of them extended communities, as we know from other VPN technologies. As of today, DEANA already assigned 11 different route types to use in EVPN stuff, and we might see on the next slide why we actually need this many. There's a constant stream of new RFCs and stuff that is actually being added to EVPN. So far, we've only talked about the control plane. EVPN is actually designed to handle different data planes, which is different than most other VPN protocols we've seen before. The original RFC already talked about MPLS as a data plane. There is an RFC from the same year that uses provider backbone bridging as the data plane. Yes, somebody was actually brave enough to build an implementation around that and run a whole Olympic event with that. Avaya back in the day, who remembers Avaya when they were still doing network stuff? But yeah, they did. And then something which was quite revolutionary, network virtualization overlay, an RFC extension from 2018, which brought us all of the fun of VXLAN, NVGRE, Geneve, or whatever IP-based overlay technology you might think of. So it opened the door to actually have IP-based data planes as well. What do we actually do with this fancy protocol? So the initial draft, as I mentioned, it tried to mimic an ELAN service. Your service provider net becomes a big switch. Well, who doesn't want that? Well, if you need that, you know. If you don't need that, forget about it. It was built as a VPLS successor. VPLS already came in 2.5 different flavors, BGP signaled, LDP signaled with and without auto detection. So it was already a mess, and this tries to bring that together. It at least attempts to solve a couple of the challenges that the preceding protocols had. Data plane learning, I already briefly covered that. It's a control plane-based data learning. It covers multi-homing, it covers auto detection. It's used in service provider networks with the MPLS data plane, and that's where it probably became most famous in data center networks in conjunction with VXLANs. We now suddenly route and have overlay networks in our data centers. It can also be used as an IP-VPN. The original RFC already had all of the building blocks. One of the route types, type 5, carried routing information. By something called type 5 only, you can mimic an IP-VPN on EVPN only. Remember the Ethernet part of EVPN? It somehow involved MAC learning. You can forget most of that and do just routing. Combine that with VXLAN, and you suddenly have IP-MPLS VPN capabilities in your data center. Quite fancy.
There's gateway implementations. If you still run traditional IP MPLS VPNs, you can have interconnecting gateways depending on your vendor of choice. We also have a virtual pseudo-wire service, ELINE service, a point-to-point service since 2017. It aims to be transparent, be point-to-point. It inherits all of the multi-homing capabilities that EVPN already introduced in its original protocol, which is kind of cool. It was typically a hack for most point-to-point protocols to have that. And it introduced the capability to have a pseudo-wire per port, per VLAN, and per group of VLANs. Doesn't seem like a solution yet for the problem we had earlier, because that's where we started. If you're unfortunate enough, you might even need multicast stuff in there. First of all, if you actually need to do that, well, my apologies to you that you actually have to deal with that stuff. I fortunately never had. There's a lot of RFCs, a lot of different ways to do that. We are not covering that today. If you need that, you will know where to look at. These two slides didn't do any justice to the protocol. Very brief rundown, no real deep introduction. There's a lot of material available. We had talks on DENOG, on other NOG events, on RIPE events about that, so go find them. You'll even find me talking about that in my past employer's role on some YouTube videos, so you will find resources. There might even be a talk in this conference which is about EVPN. I haven't memorized it completely, but there's a high chance there is. Okay, EVPN Flexible Cross Connect. What's this all about? The smart guys building the RFCs, they identified a problem. First of all, the full name of this new fantastic protocol is EVPN Virtual Private Wire Services Flexible Cross Connect Service. So remember that, we are doing a test at the end. It's a RFC which was finalized in 2025, in March earlier this year, but it was worked on for a very long time. The main problem statement in this RFC, the service providers which are actually writing this RFC want to multiplex a large number of ACs. ACs are attachment circuits, so basically stuff that goes into an aggregation device, across several physical interfaces, sounds familiar, into a single VPLS service tunnel to reduce the number of service labels, resources and scale, and to reduce the number of eBTP signaling, because you might not need to signal every individual AC as it was in the old draft. How does it do it? It isn't really revolutionary. It uses a quite simple trick, but we'll look into that. We apply a bit of magic. There he is again, our friend, the aggregation router. He needs to learn a couple new tricks right now. And yeah, the main trick is, on any given interface, you have a number of VLANs. That's what you see at the bottom left corner of this slide. Those of you who are into service providers might know you have outer and inner VLAN combinations. And the trick that the device doing virtual pseudo-wire services with flexible cross-connect is, it now needs to normalize these VLAN IDs, called WITs in the standard, to create something which is called normalized WITs. At this point in time, the guys in the RFC took a shortcut and basically wrote a sentence, yeah, how this is done is up to the implementation on the devices, do whatever is needed in order to create unique VLAN IDs for the normalization part. You can do swapping, you might introduce a third or fourth VLAN tag, whatever you do. Once you chose your normalized WITs, they need to be unique. They will be put into an EVPN route of a specific type, an AD route, and they are signaled to the other end, which ultimately maps into one pseudo-wire. It's cool, but it also has some challenges, as we'll see later. A more specific example, how does this actually help the case that I tried to build up? Again, our aggregation router, it's now scaled to 8 interfaces with outer and inner VLAN tag combination. Let's assume our aggregation device is smart, is capable enough to do layer 2 VLAN magic for whatever we want from him. What we could do is, we could tell the EVPN Flexible Cross Connect service, take interface 1 to 8, take the outer VLAN range 1000 to 2000, normalize that, and put that into an EVPN pseudo-wire service towards destination 1. We can then take, again, all of these ports, outer VLAN range 2000 to 3000, normalize that, do whatever it takes in order to do that, and map that to a second pseudowire or a second service instance towards another destination. And we are already halfway there where we wanted to end up with. Obviously, nothing is easy. So when you write an RFC, there's not only one way of doing that, there's typically multiple ways. So the next slide covers the two modes of operation that these guys invented in order to do so. There's a default flexible cross connect. Sounds simple. Whenever you attach one circuit or one interface to an EVPN service, it creates the normalized VIT, and it sends a route to the other side of that service. From this point on, that service is instantiated and forwarding data. Whenever you add an additional AC, there's no new EVPN route, there's no new signaling of all of that. It will just assume you did the right thing and configured the appropriate interfaces on both ends. And it will just happily start forwarding for all of them, or fail to forward if the other side isn't already set up. You might need multiple instances in order to have different destinations to map your attachment circuits in, but even in that very simple form, you already have the opportunity to map multiple physical interfaces into the same service. Unfortunately, as I mentioned, there's no additional signaling, so the boxes will never know that somebody configured something which isn't right. So the guys thought, well, we can do one better. And they also introduced something which is called VLAN signal flexible cross connect. Same idea, but now we send one route per VIT that we attach to one of these instances. We can get away with only having one instance, because in theory, every one of these route advertisements could actually signal a different pseudowire, but we are free to actually select multiple EVPN service instances. And as we are signaling each and every attachment circuit and every combination, there is a way for the device to at least warn or prevent you of bringing interfaces up. This depends on the implementation and what the vendor actually did. So you're basically trading one route per instance versus a lot of routes per normalized width, which obviously could boil down to a scaling issue as well, so you're free to choose which direction you want to go. You want to be a little more secure that everything's set up, or do you want just to make it work? Having learned that protocol, let's have a look at a potential solution. Everybody still remembers the problem, right? This is the number of pseudowires we had in our old world. And let's now rebuild the same scenario with EVPN Flexible Cross Connect. Again, same assumptions. We have 3 target categories. We have our aggregation devices. We have 24 ports per aggregation device. And we have a lot less pseudowires we need to take care about, because in theory, it's an idealized solution. Your mileage might vary depending on how your device actually handles the situation. You couldn't end up with only 3 pseudowires per aggregation device, because you have 3 destinations you want to reach, and you can map all of your interfaces and that in there. On the BNG side, you only have 1 per aggregation device. Everything is nice and fancy. And obviously, this is the marketing thing that everybody wants to know. 95% of reduction in pseudowires. So put that on your data sheet and go out and market for that. Is this actually working? Is this available in the real world? The draft is only from March. Well, it is. As with a lot of these EVPN things, people started to implement it way before the RFC was finalized, because typically these EVPN RFCs are kind of pre-agreed on once they're actually entering the standardization process. So a lot of people started to actually implement it. I do have personal experience on Juniper and Arista devices, both before and after the RFC was rectified. And in general, the interop basically just works. There's the typical quirks. If you apply fancy knobs, if you do random MPLS label insertion and stuff like that, if you play around with ether types, if one of the side is default, what the other side is VLAN signaled, obviously they might not really come together, but generally it works. Think of what you watched from the ENTC interop test. They actually tested this year as well for the April MPLS Congress, and they also found it successfully working between the existing implementations, which were Arista and Juniper, surprise, and Sienna, which was a bit of a surprise. The actual usefulness highly depends on what your vendor or your network operating system actually allows you in terms of layer 2 gymnastics. As mentioned, the RFC just tells you, yeah, your device needs to handle that. So if you need this normalization, you need to have chips in the boxes that can do that, you need to have a NOS that actually takes care, and you need a config layer that makes sense. Vendors with very flexible layer 2 config options might be an ideal fit for that kind of solution. The last sentence on that slide is a completely personal opinion of mine. The Arista Flex NCAP thing and the unmatched option, I'll explain that in a moment, is more or less ideal for that. The unmatched thing allows you to configure a couple of VLANs, map them into services, and just put unmatched for everything else on that interface, which is then mapped into another instance. On other vendors' boxes, you might have explicitly configure each and every one of these missing VLANs, which first of all take place in the ASIC and in the forwarding logic, and also introduce work, because you later might need to change that, because it's no longer in that instance, but in that instance. And if you do that with default, there's nothing which actually prevents you from making mistakes there. The Nokia implementation probably will be up to speed with their service access point stuff, because they have flexible matching in there as well. I spoke to the Nokia guys. It was implemented in basically the latest release for SROS. I haven't touched it. If you have, please find me and let's talk about that. Is anyone actually brave enough to use? Yes, we are. We actually use that in our network as of today. We are backhauling various services towards our BNGs. We are not using the full potential of that protocol yet, but it generally just works. We mainly deployed that on our Juniper network, but we're mixing in a couple of Aristas as well. And we continue to migrate from LDP-based pseudo-wires one after another while we are raking through our access networks. Be aware, I covered that. Your vendor's implementation might not be very obvious which of the modes it actually uses. The Juniper documentation has one side note in one sentence, which points you towards you need to create individual instances, which, now that you have seen the presentation, basically means they are using the default mode. They're not explicitly saying that, at least in the older parts of the documentation. They're now updating the documentation and it becomes a bit more obvious. If you already used it as well, come find me. If your vendor have an implementation that I've not covered or not seen, find me as well. And from a content perspective, that's actually it. So that's what I wanted to bring across for today. First of all, thank you for listening. If there's any questions, I understand we have a bit of time for them. So if there's any, now would be the time.
Thank you, Tobias, for the talk. Yes, we do have another 5 minutes for questions. Please state your name and affiliation each time.
Hi, Silvan from Open Factory. One question: I have seen in EVPN implementation the way to do LACP single link on one chassis, and then the end device has LACP. Is there a way to do that with the pseudo wires as well?
The multi-homing part can consume everything that EVPN offers. It can do multi-homing via LACP, via the back-end EVPN channeling. If you are brave enough to have actually read the implementations, there's even STP-based multi-homing implementations in the RFC. Luckily, I've not seen anyone doing it. But yes, that's the idea. Pseudo-wires can make use of that multi-homing. You can have 2 or even 3 endpoints for your pseudo-wires attached to a network. I've not seen one brave enough to do active-active for that. So far it's active standby, but in theory it would be possible, but yeah, loops may happen if the rest of the network isn't aware of that.
Okay, other question in the room? Otherwise we have one on Venuless.
So from Markus Bauer, we came from a place with RSVP underlay where we need to configure LSPs on PEs before configuring pseudo-wires between them. We got away from this complexity by using a segment routing underlay. Now we are moving this function to the next higher transport connection. And we need to make sure this connection is configured on participating PEs. Your setup on this level is pretty simple. How do you expect this to grow in the future? And do you foresee a time where this technique might become too complex in your network as well? Thanks.
Yeah. I mean, every tool you have in your tool chest has to be selected for the appropriate use case. If you're really into nailing down traffic engineering path, I mean, EVPN isn't the place to do that. It's already mentioned, it's SR with key extensions. I don't actually see it's complex from the configuration point of view. The configuration point of view actually becomes a little less complex. Debugging that stuff might be a bit more involved because you need to understand more of that happening. If you're using the per VLAN mode, you need to understand that the appropriate EVPNs are, and it's a point-to-point technology. So there will always only be 2 endpoints, or if you're using redundancy, there might be redundant endpoints. So I don't really see it becoming too complex or too problematic. But yeah, as mentioned, if you're using a tool in creative ways, creative things might happen.
Okay, thank you. Any other question in the room? No? Then we close that talk. Tobias, again, thank you very much.
Thanks, guys.